Okay, so maybe we'll start our last lecture. I thank you for sticking with it for this long. For this last lecture, I want to kind of double back and revisit L1 problems. But what I want to talk about is just some interesting ideas that some of the people in my research group have been having about what happens when you have streaming data, right? Or what happens when you have some dynamics involved with your system, right? And so what I mean is we have this kind of a notion of doing signal processing now, or signal recovery by doing L1 minimization. Right? So I have some observational model phi, I observe y, and then maybe I want to solve this regularized optimization problem, right? So we spend a lot of time talking about min xl1 such that phi x equals y. This is almost the same thing. It's kind of just a relaxed version of it. Okay, and so that's kind of what we do. But what we do is kind of think about this more in terms of a filter, right? So in this case, what we kind of have here is we have these measurements y coming in, and I solve this optimization program, and then x comes out, right? And so that's a fine construct, if you just stop it at that. But what we want to do is kind of not make this static. We say the input's changing all the time, right? I'm getting new input all the time, and the output's changing all the time. So how can I think of this more kind of like a filter? I have multiple input, multiple output. This system is trying to do something like that with phi. And how can I sort of make sense of this? Because this may be what happens in, maybe not everywhere in the real world, but say in many applications we're interested in. We have measurements streaming off of a radar that we're continually trying to update what our view of the world is. We like to do this in kind of an efficient manner, or a principled manner, if you will. Okay, so we're going to talk about two different ways to think about this. So one of the ways is the sort of the baby of my first graduate student, so Salman Asif. So he wrote his thesis on how do you quickly update the solutions to L1 optimization programs. So here the idea is, I have I have the solution to this problem, and then I learn something new. So I get a new measurement y, or a new set of measurements y. And maybe how do I update my estimate of what x is? And then maybe x is moved in the meantime, right? So maybe I have some dynamical model for how it's moved. So maybe can I do something like a Coleman filter, where I just have an efficient set of updates to get the new solution back from the old one. So what he did in his thesis is kind of develop, not just how to do this, but really a framework for doing something like this, for L1 problems in particular. Okay, the other aspect that I'll touch on is work by another one of my graduate students and another professor at Rice, Chris Rosell. And that's basically really do treat this as a continuous time system now. So, we've looked carefully at dynamical systems that if you feed them with a y and they hold it steady, eventually they settle to the solution of this, right? And so what's the kind of the convergence behavior of these dynamical systems? And then, ultimately we understand how those things move as we change these y's. So it's like dynamical systems that do sparse recovery for them and understanding how those things behave. Okay, so let's talk about this first part, this fast updating part. I probably won't go through all of these slides, just the ones that are kind of relevant. And it's a neat idea because it kind of ties back to I don't know, when I teach, for some reason this is one of my favorite things to teach, this idea about recursive least squares and Coleman filtering. So the idea is let's say, here's the classical problem. So let's say I have the phi is full column rank. I've observed y equals phi x. X is arbitrary. I just solved this least squares problem, x hat. And in some sense, this is my best guess for what x is, given what I've gotten for y. Right? And so now what happens, I have this solution in my hand, and now I say, okay, let's say I make one more measurement. Right? I just add one more row to phi, so I learned something new. What's now my best estimate for x? Right? And so what's really neat is I don't have to recreate phi and recreate phi transpose and resolve it all. there's sort of a systematic way to do it. So what I can say is, okay, look, I want to do the same thing. I want to find phi transpose phi minus 1, phi transpose y, but now phi is a row bigger. So I can sort of rewrite this as phi transpose phi plus phi t minus 1. Now, it just turns out that I can, if I have phi transpose phi minus 1 in my hand, I can use a low-rank update to compute what this new inverse is. In fact, you don't even do that. You can compute what the solution to this new system of equations. And like, what does it look like? There's a kind of a nice interpretation to it, too. It says, okay, well, my new estimate is going to be, it's going to be my old estimate plus some updating matrix times the difference between what my new measurement is and there should be a hat here. And what I would have guessed that new measurement would have been for my old measurement. Right? So it means like, if my new measurement matches my worldview of what x naught is exactly, this is 0, and I don't update the answer at all. Right? But if it's different, I update it, and I update it by pushing it through a linear filter, and then there's a nice expression for that. But notice what this filter contains. It just contains phi t phi minus 1, which I already have sitting in my hand. And then this is just a number at that point. So this requires applying phi transpose phi to a vector, corresponding to a new measurement, and then solving a new system, applying phi transpose phi minus 1 to that new system. So with the previous inverse in hand, the update basically has a cost of a few matrix vector multipliers. So it's like a very beautiful thing, this recursively squares, right? And it really works basically because of two things, because the solution is linear, and that we have this beautiful low-rank updating formula, right? We can turn this into this, or this is how we do an update. Okay, and that's good. Another thing that's classical and very nice is almost the same thing, but now it's like I observe something of x, and then I get a batch of measurements at time t equals 1, and then a new batch of measurements at time t equals 2, but in the meantime, x is moved. So I'm really measuring two different things at time t equals 1 and t equals 2. But that doesn't hurt me that much, because if I have a dynamical system, I have a model for how x moves. Right? So this is kind of like, these sort of classical problem in control theory here. Setup and control theory. The idea is like, the thing I'm trying to estimate, x, it's evolving according to some linear dynamics, possibly with some errors, and I'm making observations of it each time through a linear system. Right? And so then the question is like, how do I sort of optimally estimate these x at all times? Well, one way you can do this is you just set up this giant kind of systems of equations. I can say I want to estimate x given all this stuff. I can just sort of rewrite this into one big matrix equation and solve for x1, x2, x3. So really what you're doing here is you're finding the x, which sort of jointly minimizes the sum of errors over all time. But you can also do it very quickly by doing this recursively, right? So this is what you would call the Coleman filter. So again, there's a way that given these new set of measurements, right, what I say is, okay, look, I want to update my current estimate for what x is, so I look at the difference between what I measured and where I would have predicted x would have been for my measurements, if x would have been if I had just updated my old system with the dynamics, and just pass that through a linear matrix. So again, I can compute this, again, using all low-rank updates. Right? If I get a small number of measurements, the cost of updating the solution to this optimization program really does just scale like a small number of matrix vector multipliers. Okay, so these are two beautiful classical least squares things that tell you how to update solutions. So it's kind of like what we want to do is how can we get something like this for this L1 problem? Okay, so we can do it almost. But it's not. So that's what we do. So we want to dynamically update the solution in several different situations. So one is like, the signal x changes slightly. And I'll talk about that case in detail, and then the rest of the stuff you can almost use your imagination for. The second thing is maybe we add or remove measurements. Right? So I learned something new about x. How do I update the solution? One thing you say is, okay, look, maybe I have some weighting of x. So maybe instead of just lambda x1, maybe I have like I weight all the different entries in x differently. So maybe W is a diagonal matrix with positive entries in it. What I'm sorry. What that's kind of saying is maybe I favor some of the coefficients for x being more active than others. But then maybe the way I want to express my knowledge about the changing environment is through these weights. So maybe can I quickly update the solution to this program as these weights change? And then, again, if we have this kind of Coleman filter set up, we have streaming measurements and an evolving signal. What can we do? So it turns out we have kind of a framework for doing all these things simultaneously. And let me just try to give you a flavor for what that is. And here's how it works. So obviously, one of the reasons the Coleman filter and recursive least squares works is that the estimate is linear in the data at the end of the day. And that's just not true for the lasso. But it's true, almost true, in kind of a local way. All right, and so here's how it's almost true. It's true that if I just write down the optimality conditions for this program, right? So remember, when we were talking about constructing the dual certificate for L1, it's almost exactly the same thing. So basically, I look at, when the derivative of this is equal to 0. There's no such thing as a derivative because this guy's rough, so I look for a subgradient of this. So I say, okay, what this, x is the solution to this. If the subgradient at x has a 0 in it, and the conditions for that happen to be, x star needs to obey this. So if x star is supported on gamma star, it's a solution if these two equations are obeyed. Now let's not get too much into what those equations are, but what's the thing to notice about them is this is a linear condition on x star, right? And what it really is a linear condition on what x star has to be on the support of x. And this is a linear inequality constraint on x star. So we don't have linear conditions, but we have almost linear conditions, like linear equality and linear inequality constraints. And so that's basically what we can use, the fact that these are linear to, again, translate updates into a series of low rank updates in the matrix sense. Okay, so that's what we have. So these are the sort of the optimality conditions for being a solution. And kind of everything we do can kind of flow from these. Don't worry too much about, that these look complicated. Just the main thing to note is, they depend on what the support is, right? And they are linear on the support, and you have nonlinear inequality constraints off the support. So it's exactly the kind of stuff we were doing the other day. Okay, so here's an example of how you proceed, how you exploit these types of conditions. It's a very simple one. So let's say I observe y1 equals phi x1 plus e1, and then I solve this optimization program, and I have some solution in my hand to this, right? Okay, so I do that, and that's great. And then the next thing that happens, I get a new set of measurements, and it's of a new signal, phi x2 plus some more error. And now what I want to do is I want to solve this same program again. Now the idea is look, okay, I can take this new data, I can go resolve this problem and get a new answer. But the idea is if I say okay, maybe x1 and x2 are close together, so maybe these estimates should be close together. Maybe I don't feel like I should have to do all this work by resolving this optimization program to move from the solution of this to the solution of this. So here's one nice thing you can do, and this is actually almost the same trick you can play in all of these things. And you can do something called homotopy. And that's, what homotopy is a sort of general word used in mathematics where you kind of map one solution into another solution. And as the problem changes, you track what the path of solution is from one to the other. So let me explain in this context. What I do is I just look at this optimization program for all epsilon between 0 and 1. All right, so when epsilon equals 0, I am at the solution to this problem. Right? Now as I change epsilon equal to 1, right, this guy goes away, and I'm at the solution to this problem. Right? And so what the idea is okay, if I know the solution here, let me change epsilon slowly and see if I can track the solution as I change epsilon from 0 to 1, thus moving from the solution of this program to this program. So that's the basic trick. And what makes it nice is this fact that we have linear conditions on optimality. Okay, so here's what you can do. So say, let's just write down for a fixed epsilon, what does it mean to be optimal? Well, it's exactly the same as before. It's a set of linear conditions now that involve epsilon and those sets of measurements, because this optimization program involves epsilon and lots of old measurements. But at the end of the day, it's this, right? And so for epsilon really small, what does it mean? It means, okay, look, the direction I'm going to move as I change epsilon It's basically this matrix times the difference of these measurements on the support and 0 off the support. So the point is, I just look at the optimality conditions and it gives me a direction to move. And the other point is that this direction is linear in the measurements. Right? And so what you could say is, okay, I move in that direction until gamma changes. Right? And so that's the idea. It's like I move it, so I'm at this point, I look at epsilon, I figure out a direction I need to move. That direction depends on the support I'm currently on. And then I move in that direction, and since it's linear, I can do that very quickly. And I do that until one of two things happen. One of my things on my support goes to 0, so the support changes, or one of the constraints that I have becomes active. Right? So that basically means I need to add or remove something from the support. So what you have now is you don't have like a linear step from the solution of one to the other, but rather you have a series of linear steps. So basically, if I'm sitting here, I say, okay, change epsilon, I have to move in this direction. I can very quickly calculate how long I can move before I constraint gets broken or the support changes. And I can move from here to here, and then changing direction, since only one thing in the support changes, it's a low rank update. So it costs me, matrix vector multiply, low rank update, matrix vector multiply, low rank update, etc. So instead of just one low rank update, you just need a sequence to move from one solution to the next. So it's a nice thing, and then you can run experiments to see how well it works as you do things like we have like a 1D signal that we take to just be different rows, scanning rows of a house, so it's changing slightly, and then sometimes really abruptly, and then talk about how efficiently those update versus other warm-started optimization algorithms. And the point of all this is that it works well. It works better than taking a state-of-the-art solver and starting it with a warm start from the other thing. Okay, so that's the kind of the trick. You can replay the trick by adding a measurement. So here, the epsilon just comes in, adding a new measurement in the file. Right? So that's kind of like the recursive least square set. So you get the path, and we get a bunch of results. You can do the same thing with changing the weights. Right? Again, what you can do, it's kind of been shown that if I solve weighted L1, it can help me in doing some sparse recovery problems. But again, you can set this up as just this one of these sort of homotopy problems where I slowly change the weights. I get a direction in which to move, and then it's again piecewise linear sequence of updates. It works really well, much more efficient. The sort of point of these graphs is much more efficient than just doing a warm start. Okay, so. Finally, we can also do things like Coleman filtering, right? And here the trick is like, we're not only adding and removing measurements, we're not just adding rows of the file, you're also kind of adding columns. When you add a new frame, it's like you're measuring something new. There's you get x1, and then you get measurements of x2. So the number of things you have to estimate is increasing at every step too. Okay, so not to go into it too much, but one way, way you can come up to solve this, and actually a way to solve almost any of these problems. You can sort of recollect all these results into one general framework. Because you can say, okay, look, let's say I want to solve this program, period, right? And let's say I also have a guess, and I'll call it for what this solution should be. That's kind of the common theme is in all of these different things. This is a general way I can take a guess, like warm start from a guess, and then set up a homotopy formulation to go to my new solution. And the answer is yes. Like all you say is, if I want to solve this program and I have a guess V, all I do is I say, okay, look, I can choose a U such that my guess V is the solution to this program for epsilon equals 0. Right? And then as epsilon equals 0, I phase this out, go to the solution of the program I want, and I can trace that path being piecewise linear. So this vector U just depends on your guess V in kind of just a straightforward way. Just ways, again, this all just comes from the optimality conditions. Okay, so that's, what you get at the end of the day. You figure out how to update these things. And so where this comes into play is like, we have like, say here we have this signal, and it has kind of like dynamic content in it. So basically, if I look at this thing in this lap orthogonal transform domain, so again, what I'm doing is I'm sort of taking a window here and looking at it at several different frequencies. So here are like the window functions, and then I look at it and modulate those windows by several different signs. Here's like the time index, and then here's like so here are like the expansion coefficients. So here are like different window times, and I just have different frequencies at different times. So it's like how do I kind of track what's going on here? So the idea is like I get measurements of this thing streaming in, and I just want to continually update the answer, and I just do so by, I have some prediction V that is based on, what my last estimate was and what the dynamics was. I set up this optimization program, then take epsilon from 0 to 1, which just gives me a series of low-rank updates, and then solve. So basically, you can solve streaming problems like this. So the idea is, if you have overlapping blocks of measurements, you want to continually update what the answer is to like these L1 problems. This is just a framework for being able to do that. Okay, so it's like streaming L1 recovery. And again, the point of the exercise is it's kind of a good idea in that it works better than other ways you might think of to solve this program, like warm starting optimization programs in the right way. Okay, so that's the basic idea for these. So that's nice in that, like, what you kind of have there is you kind of, okay, look, this idea that I have this recursively squares and the Coleman filter, that's based on having linear systems of equations. And if I'm interested in least squares, the solutions are also linear. So I can couple that with this idea of low-rank updating to get a very efficient updating scheme for when I see the measurement. For the L1 case, the mapping, I still have linear measurements, but the mapping from the solution, from the measurements to the estimate is not linear. But we see because of the optimality conditions, I can kind of treat it as piecewise linear. So that we can play the same kind of tricks, but that we have a series of low-rank updates instead of a single one. Okay, so that's one kind of aspect of dynamics. So let me just tell you briefly about another project we've worked on too, which is different, but maybe has a lot of some of the same themes. So the idea is this. So we have this motivation here. I don't know how convincing it might be, but here's the idea. It's like what we want is to kind of solve this optimization program in analog. So we want to build a circuit where we give the circuit an initial condition, and it uses physics to find the solution to L1. And so the idea for doing that is like, look, I can sort of build machines that will sort of say do things like do the key operations that we need. So do things like matrix vector multiply. Just say matrix vector multiply, since that's most of what goes on. I can do that has, let's say, a little bit noisy, but extremely low power. So like thousandths of a power, maybe what I can do on a digital computer. So that's motivation, but just more to the point, it's like, what we're kind of interested in from a mathematical standpoint is, having a set of dynamical equations, so a dynamical system, a set of differential equations that solve problems that look like this. Right? So the idea is, when I plug this into so when I try to solve something like this on a digital computer, what do? So I get in Y, and then I do some kind of iterative algorithm that's kind of like, applying phi and doing some thresholding, and, I march along the series of discrete estimates until I reach some termination condition. So now it's kind of like what we're thinking about is like, okay, I have this vector Y, and I use that as a set of initial conditions in some dynamical system that I have. So I set the vector Y, and then I let it go. And then the system evolves in continuous time. And eventually it should settle to the solution of this program. Or more generally, I can think of any kind of separable penalty for my, instead of L1, you can think of this as the sum of any function of the xn. So any element-wise norm or whatever you like here. Okay. And this came about, analog computing, one way to think about it. Another of these is kind of like people sort of thought like these type of equations are almost what you see in neural nets. They're neurologically inspired. Basically, the architecture is very simple. So it's basically you just do things like, again, vector matrix multiplies, simple thresholding devices, then feedback through this matrix. So what it's saying is like essentially just a sort of feed-forward neural net implementation of this system of dynamical equations. So again, it's almost like you're doing, if you look at this thing, this is just a thresholding to gamma. It's almost like you're doing iterative soft thresholding, but in continuous time. You keep getting continuous feedback from the state back into the matrix. So it's like continuous time soft threshold. It's almost what this is. All right, so then, what we kind of asked ourselves is like, a couple key questions. One is like, when does this thing converge, and how fast does it converge? In particular, how fast can I say it converges if I'm trying to do sparse recovery with L1 minimization? And so we have answers to these questions. And one of the nice things is, so the first answer to the question is like, when does it converge? And there's a set of very mild assumptions that you need for it to converge. So basically you need, this thresholding function. It has to be within this kind of like red window. It has to be monotonic, and its derivative can't grow too fast. But if that's true, I mean, you can show that this x of t converges eventually. So what we see here is like just a path of, say, two of the states. And the idea is that kind of no matter where you start them, they always settle down. And it's interesting to see, like, even if the solution to the lasso is not unique, which you can make it not unique, you don't get like kind of oscillations. You do get that this thing will settle to a particular solution. So it's actually very stable from the dynamical systems point of view. Okay, and there's different ways to act. I won't go through this. All right, so another thing you can say in doing this is you can say that, okay, look, that's one thing to say it converges. Another thing is to ask as well, how fast does it converge? And this is where you kind of get an interesting connection back to other ideas in compressed sensing. So one thing you can say is like, look, I can get exponential convergence if you can guarantee me that like every set of nodes that becomes active in my entire evolution, when I look at phi applied to any vector on that support, it's actually embedded. Right? So what it means is kind of like, if I can get, in some sense, if phi obeys some kind of restricted isometry property over the spaces of things that I visit, I can get this exponential convergence. Okay, so that, what we might like to say is, okay, say I'm trying to recover a sparse vector. Can I guarantee that not too many coefficients become active at any one time? That would mean that, if I had this sparse rip, that I could say something about the convergence. And so you can say something. So you can, we have, this is a weak result. We have strong result that says, like, look, if you have a random matrix, and you have a number of columns of that matrix, which looks like some sparsity S, the same result we need for perfect recovery. What we can say is, like, for sort of reasonable values of thresholds, we can say the size of the active set is kind of no bigger than twice the size of the solution set. Right? And so what that means is, I have a guarantee of exponential convergence for these types of signals. Okay, so really what the overall point is like, what we have here is kind of an understanding of basically, or a beginning of an understanding of like how we treat systems like this, but not in such a way where, again, it's not like we have a batch input, so we take some kind of digital input and work on it until we produce something out. It's like we have continuous time signals coming in, and we have a solution settling as a function of time. So it's really more like operating on the continuum than operating from batch data. Okay, so that's where I'll end. That's just kind of supposed to be a brief overview. I thank you for your patience, and if you have any questions, I'll be happy to take them. So, thank you.